Good afternoon, ladies and gentlemen. Welcome to my presentation. So the title of our work is Lightweight AI-Driven Real-Time Intruder Detection System for IoT-Enabled Smart Meter. So my co-authors are Dr. Aladdin Mayhoub, Associate Professor at Qasim University, and Dr. Moaz Krishan, Associate Professor also at Abha University. Today's agenda is as follows. I will start by motivating why we are doing this work, and then I will describe the architecture of the IoT-enabled smart meter and with different functionality. Then I will summarize the different cyber attacks that occur on IoT-enabled smart meter with the electricity, with the sense of electricity issues. Followed by contribution and summary of related works. Then I will describe the IntruderDetection system using machine learning deep learning, implementation results, and there I would describe the different types of theft that we have generated for training the algorithm, and also for I will report these results on the deployment on edge device using Raspberry Pi, and then I will conclude the presentation. Now, if you look at the current status of the grid. There is a migration from the traditional grid into the or conventional grid into the smart grid. So the smart grid has been coined in order to make it more efficient, less polluting, and also will integrate renewable energy to reduce the cost, and also to increase the, especially in Africa, to increase the number of people who will be benefiting from the electricity. So one of the key features for the smart grid is what we call two-way communication that allows communication between the utility and the consumer. In all times, it's only unidirectional, which means that the communication is done from the utility towards the consumer. But now the consumer will be able with the smart meter to have also the communication from their side into the utility, for example, in selling excess power in case the consumer has renewable energy installed on their premises. So this type of the consumer is called consumer because it can play the role of the producer electricity, and also consumer the electricity. So as a matter of fact, in 2023, there are over 1.6 million smart meters installed, and each country now they have planned to migrate from the old meter towards the more smart meter. And the smart meter is smart because it is based on a better system. It has a communication possibility, but it also has support of different functionalities. So this is the I would say the summary of the architecture of the smart meter. I took this from Toshiba. Of course, in our work we have already implemented smart meter in addition to the smart plug. So shown here in the middle is the embedded system. It's based on TMPM 061 processor. It has precision sigma delta converter. It has also power calculation engine. And you can see here on the rightmost, it has the communication units, and it supports multiple communication protocols, one for the area network, and then for the neighboring area network. I will take later on relationship between this or that. And it measures the current and the voltage. And this measurement will be treated here to take necessary actions and also to report different activity either to the user or to the utility company. So some of the key features of application of the smart meter, including real-time data collections. So real-time data collection. So here, which means that smart meter measures and record energy consumption real time, or nearly real time, which will provide up-to-date information, electricity, gas, or water usage. In our case, we are only concerned with electricity, and the future will be also integrating gas and water. Two-way communication, I already explained this. Accurate billing, it will provide precise data on energy usage. So there is, it will eliminate the need for estimated bills. I know, for example, in our country, we receive one correct measurement, and the other will be based on estimate. So here, the accurate billing is very important because it will not either charge more for the user or charge less for the user. So it has to, user has to really pay for the exact amount of energy that he or she consumes.
Time of use pricing. This is a part of the demand response schema. Outage detection and notification for the power quality. Energy usage monitoring. Remote disconnect or reconnect. This is basically for the maintenance or user is not paying on a regular basis in speed. These are the so the company will be able to remotely disconnect or connect the user. Support for renewable energy and power quality monitoring. So these are the essential functionality of the IoT-enabled smart meter. Now, the typical cyber attacks that occur on the smart meter are summarized in these slides. So here it is number one is data interception. So the attacker intercepts the communication between the smart meter and the utility provider to steal or manipulate data. So if I say steal or manipulate data, so here the data is the energy consumption, either the average or the instantaneous. So if this value has been manipulated, then all the remaining algorithms that are built on having this measurement from each user, then will produce very inaccurate results, will cause the instability on the grid, or it will also cause the failure on the grid. Man-in-the-middle attacks. So in these types of attacks, the attackers intercept and possibly alert the communication between the smart meter and the utility provider without either party knowing. Denial of service attack, DOS, or sometimes we have distributed denial of service attack. The attacks flood the smart meter or the network with excessive requests, causing the system to become overwhelmed and unable to function properly. Firmware tampering, because the smart meter relies on the embedded system, and the embedded system runs on the embedded system. So the attackers can gain access to the smart meter firmware and modify it to alter its functionality, which can cause incorrect meter readings, unauthorized control of the meter, or even complete shutdown of the device. Reply attack, force data injection, and remote disconnect. These are also other types of attacks that occur on the smart meter. Now, if you look at our concern, so the concern here is on electricity theft, because many of the dynamic pricing are based on the correct measurement of energy, and so the energy theft it will report less than actual value of the energy consumption for each user. Okay, so this will cause also a loss of revenue, as reported here. So the electricity theft causes a loss of approximately $90 billion annually. So the old methods for electricity theft, including direct hooking, so cable hooking, as shown in the figure on the right hand side of the figure, meter bypassing, meter tampering, and inverting the meter. So in our work, so we are concerned with energy theft, and the contribution are summarized on the three following points. Comparative analysis of classification algorithm for intruder detection, number one. Number two, characterizing of the types of energy theft using the public data sets. So here we have four types of thefts. In addition, we have a normal pattern, consumption pattern. And the last one is implementation and testing of the intruder detection algorithm on Raspberry Pi, which is a single board computer that can mimic the actual smart meter. So the related works are summarized in the table. From this table, you can see that none of the previous work have considered real-time theft detection using machine learning algorithms. So most of them, they rely on the cloud computing. They even not discuss the implementation at the fog layer. So the component of the intruder detection system, this can be found in any operating system course. So it has three components. Number one, the sensor. So the sensor can be hardware or software, which enables the collect of different types of data. For example, network packets, log files, and system call traces. These data are later forwarded to the analyzer. So the analyzer typically is based on the machine learning. It will analyze suspicious pattern, and those pattern will be reported to the user interface. So the user interface will enable the user to view the output of the system, and also will enable the user to control the behavior of the system. This is equivalent to manager, director, or console component. Now, why we are doing intruder detection using machine learning, deep learning, because the machine learning, deep learning has been used in anomaly detection.
as the machine learning and deep learning can identify unusual pattern data. Real-time monitoring. So typically the machine learning or deep learning now can be implemented on the edge device, which will allow a timely reaction in accordance with the threats or the alerts that they receive. Scalability, machine learning, deep learning can consider different types of volume of data, and the efficiency and the security will not be affected. Adaptive learning, because the machine learning, deep learning can learn very complex pattern within the data. It also reduces false positive, preserves data privacy if we can resort to the federated learning. It can also be integrated with edge computing. So instead of relying on the cloud, we can implement this in the edge computing, and that's what we did in this work. It also enhances security because it can process complex data, and it can also detect with high accuracy sophisticated cyber attacks. Now, if you look at the architecture of the system that we have considered, so we have considered this edge computing-based solution. So shown here are the different groups of smart meter within the area or region, which are connected through neighboring area network to the cloud. And this can be, for example, a substation, and the substation will be connected to the cloud layer. Here we have the companies, operation house of the utility company responsible, for example, for billing and for the monitoring the quality of the electricity. So the communication between the fog nodes and the cloud layer is done using wide area network, and there are different protocols and different communication protocols that can be done implemented at the wide area network, neighboring area network, or even within the house that we call home area networks. Okay, so the real-time IntruderDetection is based on the tiny machine learning. So tiny machine learning is a machine learning that can fit into a tiny device for inference. So this tiny machine learning have been done based on different tuning and size reduction of the model, which allow the model to run on resource constrained devices, and also if the devices are powered by battery, the amount of energy should not be high compared with if the device is not powered by battery. And it can also, the tiny machine learning, because it has fast response time, or it allows for the system to react in a very fast way. So that's why it allows for real-time processing, which is compatible for the implementation of the edge device. In our case, this allows for real-time theft detection and alert of the user or the company. So the flow for implementing our tiny machine learning algorithm is based on the TensorFlow Lite. So TensorFlow is a libraries developed by Google, and Google has different types of packages, including the TensorFlow Lite. And the TensorFlow Lite is a tiny version of the TensorFlow. So the architecture of the TensorFlow or the flow of the TensorFlow will be in the following way. So we have to train the model of the TensorFlow model in the cloud, and then after training, we'll have to convert it using TensorFlow Lite converter, and from there we obtain Lite model with the extension .df-Lite. And then we have two things either to implement this on Android application if the system is running on Linux, or we can implement it on iOS. So for the implementation results, so the first step we had to consider the data set. So for the data set, we considered here the Open Energy Data Initiative system, which is in the US. So it's an open source, and the data set comprises the energy users of 16 unique customer types, ranging from small business to major institution, restaurant, hotels, offices, schools, supermarkets. This reports the energy consumption per month, per hour. And here we have included to have this data set compatible with our work. We have included 4 types of theft. Theft number 1, which is the gradual reduction in electricity consumption during the day. Theft number 2, sudden and unpredictable drops in electricity consumption to zero at regular intervals. Theft number 3 is reported consumption in random fraction of the actual average usage. And theft number 4 is consistent reporting of average electricity consumption regardless of the actual usage. Now, for the implementation of the machine learning, so first we have trained several trained different machine learning algorithm, and because of the limitation number of pages, we have considered only the competitive ones. So the first one is the INN, artificial neural networks, and the random forest. As you can see here for the confusion matrix, that INN has a better accuracy compared with the RF, especially when it comes to detection of the theft number 3. So the INN, the accuracy is 92%. However, for the random forest, the accuracy is 84%. And here, for example, for the normal, the random forest is 1, and the normal is 0.99. The difference is not so huge. So that's why we have focused here on the for the inference on the artificial neural networks. So to test this on the tiny device, we have considered Raspberry Pi with the following characteristics. So the processor is PCM 2835, 64-bit CPU. It runs clocked at 1.5 gigahertz. It has 4 cores and 4 threads, and it is based on the ARM-v6 instruction set architecture. The RAM size is 1 gigabyte and runs Raspberry Pi OS 64 bits. So the table here summarizes the accuracy and the precision, recall, and F1 score of between random forest and the INN. And you can see from these results that the INN has better accuracy, precision, and recall compared to the random forest. And here the peak response time is 9 seconds. However, the average is 9 seconds. So in conclusion, we have proposed lightweight AI-based intrusion detection system to enhance security of IoT-enabled smart meter. So what we have achieved as results is nearly 97% in detecting energy theft. We have also deployed the IDS on edge devices, and the response time was on average 80 seconds, which means that what we have proposed here is also suitable for resource-constrained environment. We have also improved, we have the energy theft detection using either random forest or INN, and we have seen that INN has better accuracy, especially when it comes to theft category number 2. So in the future, we have to personalize IDS model tailored to specific consumer profiles, because what we have considered here 16 types of consumers, so that we have to consider a certain profile of the consumer, and also we have to explore alternative ways like unsupervised learning and integration with the GIS for even greater accuracy and robustness. Thank you so much for your time.